good. Well, I guess we'll start in a minute. Wait for everybody else to get here.
Yeah, Professor uh Higgins was a little like overtime, so
Okay, not a big deal. I'll have a talk with her later.
yeah.
There we go. Hey guys, hope everyone's doing well. I hope you guys had a great long weekend. This was really good. Mine was too. So, all right, let's get started since it's 9:45. Right, Lord, thank you for bringing us together this morning. Thank you for everything that you do for us. Pray that you would bless us with a uneventful spring semester. You just help everything go smoothly and help us all just keep our composure and get everything done that we need to. In your name we pray. Amen. Okay. Alrighty. So first things first, I'm going to put a poll up. You guys take a second. There's going to be 2 questions. Please answer both. All right. And we'll take a couple minutes, let you guys fill that out. Just a prereq check, and you know, what could boil down to an existential question if you really want to get down to it. All right, that looks like it's everybody. Great. Thanks. Most people, I mean, it's kind of early for a Tuesday to be questioning your existence, but whatever works for you guys. Cool. Awesome. Thank you. Thank you. Thank you. Appreciate it. All right. So let's actually get started then. Right? Oop, wrong way. So what are we going to be doing today, right? So this is ETG-410, and we are going to be doing the basics today, right? We're going to go over all the logistical stuff, and then we'll get into topic 1, objectives, and we'll talk about electronic systems a little bit today. All right. So who am I? For those of you who don't know me, I know I spent a lot of quality time with the METs last semester, right? But if you don't know me, I am Dr. D. I got my bachelor's in mechanical engineering from Lafayette College in 2005. From there, I worked as a mechanical engineer at Picatinny Arsenal in New Jersey, where I designed fuses for mortar rounds, specifically mortar training rounds. And while I was there, I was working on my master's degree from Stevens Institute of Technology in Hoboken, which I got in 2007. And finally, I went to a school, you guys may have heard of it. It's in Tempe. It's really small. And I got my PhD there at ASU. My PhD is in mechanical engineering, but specifically my research was and still somewhat is. Oh, good, good. I'm glad that the lights just go on and off randomly in this room. That's okay. Um, my research was in human hand mechanics and specifically human motor control. So how do humans use their hands so that we can understand it and put that into a robot, right? So it's a control systems type problem. Okay, so apparently we're gonna do this class in the dark the rest of the time. Should be fine. Let me know if it's an issue for you guys. Right. So how do humans use their hands? How do we make a robot or prosthetic hand use that? So it's a controls issue, and that's kind of where we're going with this class. Not super in depth, but we are going to talk about control systems somewhat. Right. On a personal note, well, I guess my professional stuff still. I then worked as an orthopedic research engineer from 2014 to 2017 at Wake Forest. Basically did a lot of research with biomechanics of surgical techniques and things of that nature. Basically, if an orthopedic surgeon had an idea for a research project, my boss and I either told them, yeah, that's a good idea, or no, you can't do that because these reasons, right? That's kind of the role we played there. Then I worked as an accident reconstructionist at a place called BioRec in Tempe. And then, now I'm here, right? And so I've taught ESG-455, STG-330, MEE 460 new this semester, ESG-360, ESG-250, ETG-410, MET-213, and I'm currently the lead of BS and engineering program, right? Both with and without the emphasis in robotics. You guys have any questions about the professional stuff? You guys, probably not, right? So let's talk about my personal stuff, right? So this is my family and I. This was actually our Christmas card this year. Got my wife, Charisse, who teaches fifth grade in Chandler School District, and my sons, Harrison, right here on the left, and Oliver in the middle. Harrison is 5, Oliver is 4. I know that that's misleading to look at, right? As Oliver is ginormous, but he is the younger of the two. Harrison has Down syndrome. He is a crazy, crazy guy. This morning when he woke up, I went in his room and he goes, "Go away, Daddy, go away." So he's basically a teenager at this point, right? And then Oliver is really super into PJ Masks, so you'll probably hear me make a lot of PJ Masks references. And if you haven't watched PJ Masks, you really should. It's really good. And it's top tier cartoon, right? What do I like to do in my free time? Well, first of all, assuming that I have any free time, I like to watch football. This year, as a lifelong New York Giants fan, was very difficult. I know people are saying that they didn't deserve to get in the playoffs, and they didn't. And I agree with you that they shouldn't have gone there. I believe the whole NFC East doesn't deserve to be there. Hot take, okay? But I would have laughed maniacally had they made it. Really, I would have. It would, and then if they had beaten Tampa Bay, I would have laughed even harder. But anyway, not in the cards this year. Maybe next year. I play Xbox. Typically, either playing Destiny 2 or Binding of Isaac, Afterbirth Plus, both quality games, right? And I've got some research interests that I try to pursue while I'm, to keep myself fresh in academia. All right. So that's it. That's the who am I, right? So we're going to go through the rest of this. You guys have any questions so far? We're doing okay? Yeah. Okay. Should probably let Nathan into class. That'd probably be a good thing. Sorry, I'm running 2 computers right now, and I have the sound off on my laptop, so when people come into the class, I don't hear it. So if you're sitting in the weight room for a little while, shoot me a Discord message and I will make sure to get you in, or text one of your buddies and they'll let me know either through chat or something. I apologize for that. I'm working on it. Streamer life, right? Streamer life. Okay. So here's my office. Even though you guys aren't allowed to come to my office, you still know where it is. Here's the phone number for my office. I'm in 1344D. If you guys know where Professor Koneman's office is, I am across the hall and 2 doors down to the left if you're leaving his office. If you know where Professor Tomford's office is, I'm right across from Professor Tomford. Here's my email, right? You can also get this information in LoudCloud, right? I've got a Twitter. I don't really use it for much, but you guys could follow me on Twitter at Dr. D GCU. Discord. Discord is what we're going to use instead of Remind in this class. And I like using it. It's an easy way for you guys to get in touch with me, right? Please follow the link to join the Discord server. It's in LoudCloud. When you get there, just introduce yourself so I know which class to pop you into. There's a general chat for everybody to use, and then specific chats for each of the sections that I have. So it's a good place for you guys to be able to contact each other or me if you're having issues with homework, right? You can also send me a private message in LoudCloud, which is fine, right? Office hours, right? Done via Zoom, and the link is in LoudCloud in the announcements. Monday is 9 to 11 a.m. And then I know that says 1 to 5, but my schedule changed yesterday and I have an additional class now. So it's going to be every other day from 1 to 3. Okay. 1 to 3 every day except Mondays, which is 9 to 11. Right. Or by appointment. Right. So, that's that. Is there any questions about office hours? No. I don't know why there's an animation in there. There shouldn't be. All right. So let's talk about the plan for the semester. All right. So this semester is weird. We thought last semester was weird. This one's just as weird, right? Because why? Well, first of all, week 1 is completely online, which is fine. We can manage that and not have an issue. We know how to do that. Weeks 4 through 13, it says broadcast, but we are in room 1304. And we had 13 at some point, but we have 12. So we're just going to do regular in person. You guys just come to class as usual and come to room 1304, and we'll just do class every day. So we don't have to worry about broadcast. Last semester, people liked when I kept taping the lectures and posting them on YouTube. So I will continue to do that even when you guys are in class, assuming that we're not doing a lab all day, because that's going to be boring to have a 2.5-hour video of me not saying anything while you guys are working on labs. But just come to class as usual. Weeks 14 through 15 will be online again. We are going to have to shift some of our assignments around. I'm still trying to figure out what that looks like, so just bear with me. But that's stuff that's not going to affect the early part of the class, so please don't worry about that right now. Okay. So week 1, all right, it's happening right now. We are in week 1. What do I expect from everybody, right? First of all, that you guys come to class on time and ready to learn, right? So be prepared for activities. Typically, the way that I run this class is like the Tuesday class, we will do most of our lecture once we get past like topic 1, where we have all the definitions and things. And most of the rest of the time is you guys working on programming to the PLCs and doing your labs. This is kind of a class, in my opinion, like SolidWorks, right? I can stand here and I can talk to you and I can show you how to program a PLC, but you guys aren't going to learn it unless you actually spend the time to do it, right? So you guys are going to get a lot of experience doing a lot of programming of the PLCs, okay? So I expect you guys to complete your own original work, right? You can work together. I have no problem with that. But when you write up a lab report, right, I expect you guys to do it on your own. You're going to treat one another with respect, right? So this isn't a learning environment, right? And you want to make mistakes here. You don't want to make mistakes when it counts, right? This is a place where people are going to make mistakes. You can ask anybody who's ever had class with me. I make mistakes all the time. whether it's writing the wrong numbers down or whatever. I make mistakes all the time. Don't be embarrassed to make a mistake. That's the best way that you can learn. All right. Expect you guys to treat me with respect. I really, really want you guys to ask questions, right? If you have a question, make sure you get it answered. If you ask in class, that's great. It's typical that somebody else will have the same question. If you're not the kind of person that likes to ask questions during class, or you're like me and you don't necessarily think of it right at the time, come to office hours, right? And let me know what you're thinking and how I can help you. If you're struggling, right, I can't help you unless you make it known that you need help, right? So please use office hours to your advantage. I expect you guys to participate in classroom activities, right? So if you don't participate, then you don't get the participation points. You guys will know when it's a participation activity. We'll talk about what I expect out of participation activities as well in a second. Just some basic Zoom etiquette, and I'm sure you guys are sick of hearing this after, 2 semesters and 3 weeks of being online, right? But you guys don't have to worry about number 1 because I set my meetings to auto mute when you guys come in. So that shouldn't be a problem, but just check to make sure that you're on mute. Use your real name as your Zoom name so that I know who you are, right? Just obviously, I want to get to know you guys. I'm pretty good with names and faces. And so hopefully by the time week 2 rolls around, I'll know everybody that I don't already. Have your camera turned on, right? So black screen is going to net you 0 participation points for the week. That's how it's going to be. This means, and I know I'm evil and I'm rude, but that means you're going to have to get dressed for class. Okay. Just please get dressed for class. Use the chat to ask any questions that you have if there's not a pause in the lecture. I'm pretty good about reading chat. I got it open right there, right, and it should pop up on the screen when I get a chat. You can answer questions that I ask by unmuting, right? So that's fine, and just don't be rude. Right? Just don't be rude. All right, so weeks 2 through 13. I know that says Wednesday and Friday. Man, told you those mistakes coming through. Batting 1,000. Today's Tuesday, right? It's Tuesday. So Tuesday and Thursday, just come to class in person, both days. We are in a big enough room here that it's not going to matter. So we can safely social distance. Obviously, when we're in person, masks, right? Masks for class. That hasn't changed. So there's that. Okay. In-person expectations, there they are. All right, come to class on time, ready to learn, complete your own original work. Nothing's changed so far. Treat one another with respect, treat me with respect. And here's the red, wear a mask, right? Non-negotiable. It's handed down from on high, right? Dr. Wooden has said that if you come to class without a mask, you're going to be asked to leave until you can get one. I'm looking around this room. I think there might be a stash of masks over there. So if you don't have one for the day, I can probably have one for you. But I think at this point, most everybody's got a mask or 2 lying around. Social distance, right? So in this room, you'll see it's not a lab classroom, it's a regular classroom. So there's going to be 1 seat per table. Don't double up on seats. Don't do any of that stuff. Right. Ask questions and participate, right? Those are the expectations. All right. Is everybody clear on that stuff so far? Everybody doing all right? Yeah. Nothing. Okay. Cell phone policy, right? If I see your cell phone out, you're just going to lose participation points for the week, right? When you're in class, I expect you to have your cell phone away in your bag. Now, if you absolutely need it out, right? If you're in the middle of a family emergency or something like that, right? If you're married and your wife is pregnant and she could have the baby any day, right? You don't need to give me the specifics, but please talk to me prior to class and just say, hey, Dr. D, I need to have my phone out today. That's all you have to do, right? So just give me a heads up at the beginning of class and we'll be cool, right? You ordering Grubhub so that it'll be back at your dorm by the time you get back to, by the time you get there is not an emergency that needs a cell phone, right? But if you do have a legitimate reason, just quietly tell me before class and you can have your phone out, right? And then week 14 through 15 is online again, right? We were pretty lucky this year. We got a new software package that we're going to incorporate into this. It's called PLC Logix 5000. It actually has some virtual environments that you guys will get to program as if a PLC was controlling it. One of them being the four-way intersection with push button pedestrian signs, and it comes fully animated and everything. It's pretty neat. We'll talk about how to use that stuff probably next week. This week is more of the lead up to doing some of that stuff, but we'll talk about all the different software. There's two software packages. One is that PLC Logix 5000, and the other is RS Logix, which we'll discuss when you guys get into class next week. Okay. So more expectations, right? What can you specifically expect me to do, right? I will treat you with respect. I'll grade your assignments in a timely fashion, right? So 1 week with feedback. I will always be in my office during office hours unless somebody schedules a meeting over top of it, in which case I will give you guys notice. I'm pretty available in Discord, right? If you need something quick, try Discord. But remember, the official channel is LoudCloud private message, right? So just remember that. I respond promptly to emails and messages on LoudCloud. Like within 24 hours during the week, I check typically once a day on the weekend. So if you send me an email or a LoudCloud message, I will get it on the weekend, right? If you need me, like if it's like, really necessary, Discord, right? And I'll check that more often just because it's tied directly to my phone. What else? Yes, that's about it. Oh, typically, I don't know if this is oversharing, but typically I go to bed around 9-10 o'clock at night, right? So if you message me after that, you're definitely not going to get a response till the next day. Right, so. All right. What's my late policy, right? It's a little bit different than last semester, right? So here's what GCU's late policy is in the handbook. All assignments are due before midnight Arizona time on the due dates indicated. Assignments posted after the indicated due dates will be subject to a deduction of 10% of the available points for each day late. No assignment can be accepted for grading after midnight on the final day of class. Technical issues are not valid excuses for late worse unless the problem stems from GCU servers. Exceptions to the policy are at the discretion of the instructor, right? From the Grand Canyon University Policy Handbook, page 28, right? And that's the important sentence right there that is actually on the separate page from the rest of the policy, so it gets missed quite a bit, right? So the discretion of the instructor, and my discretion is that late work will not be accepted. Why? Because in the real world, deadlines matter. So they're going to matter here, right? Now, when it says it's due in LoudCloud is when it's going to be due, right? In this class, you're looking at the work breakdown being homeworks, which are run through McGraw-Hill Connect. So please make sure you join the McGraw-Hill Connect site. You can either do that through the link in the announcements or through LoudCloud. It is linked up in LoudCloud as well. All right, that's going to be your textbook. There are some Learn Smarts there. Those are optional. They're not graded for anything, but if you want extra material to read and work through, That's what we're gonna do. So it's homeworks and it's labs and there's a benchmark assignment, right? Um, and there's a final project. It's mostly labs. So lab reports, right? And we'll talk a little bit about lab reports because it's gonna be a little bit different than other classes. Okay, so right, participation assignments. Yeah, Logan, what's up?
It says the registration for this Connect section is closed. So I went to like go register and it says it's closed.
Okay, I will check after class,
Okay.
and I probably just didn't set the date correctly.
Okay.
I'll check in a couple minutes when I'm having you guys do the icebreaker thing.
Okay.
Cool. Thanks for letting me know. Participation assignments. What are included in those things, right? So can consist of time trials. Probably not for this class. Time trials is when I make people do a problem as fast as they can, but there's really no problems to do here. So there's that. Problems meaning, yeah. So we're probably not going to do problems. Might do Kahoots, might do poll everywhere questions, discussion questions on LoudCloud, right? These can be things that are inside or outside of class. Some occur at random, right? So typically the way I run participation is I do about one assignment that's officially participation per week. And you need to be in class and working on that participation activity to get participation points, right? So if you've got a 50-50 shot this semester, right? So if you miss one day and you miss participation, that's kind of it, right? So probably not a great idea. Voluntold. So if I need an assistant or I need somebody to answer a question, we're going to use a lottery system. So when you guys come to class next week, I'm going to have ping pong balls with numbers written on them. And each one of you will get one. And that is yours for the whole semester and beyond. I really don't need it back. It's fine. And when I need somebody, I'm just going to random number generate. And whoever's number comes up, you get to answer the question, right? Unless somebody else wants to take the burden for you, right? So that's the plan. Everybody all right so far? We have any questions? No? All right. Well, let's keep rolling. In case you guys didn't notice, if you look at the top corner, should be like up here-ish. Top left corner of your screen, you'll probably see the recording icon and a thing that says live on YouTube, right? So I know I mentioned this earlier that I post these to LoudCloud I post these to YouTube, right? There's a link to the playlist for this class. After class, when I get back to my office, I will take the video from YouTube and I'll take the live stream and I'll post it to that playlist. So you guys will have access to that after the fact. All right. Don't forget, post in LoudCloud, right? You guys have until next week to make sure you post to that initial discussion question. Otherwise, MATLAB. Otherwise, LoudCloud will drop you from the class, right?
Question.
Yeah.
Because it's like formatted as a submit something here style assignment, should we just post to the class wall or do you want us to like write up a text file?
Hold on one second. So you're saying that the discussion question is saying submit something?
Yeah, I think last I checked, it's one of those styles.
Let me just double check that. It shouldn't be. It should just be the standard thing where you just make a post on the discussion thread.
Yeah, it's happened in other classes for us before.
Super great. Let me take a look real quick. Sorry, please hold. Oh, there's no discussion question in there, huh? Well, isn't that fancy? Yeah, post to the wall, I guess. I don't know why there's no discussion question. Very strange. Post the wall. I'll get to the bottom of that by the end of today, and I'll put an announcement letting you guys know exactly what we'll get. I'll either get a discussion question up there or tell you how to handle it. But just do everything else as normal, like it's post on the wall and all the other good stuff.
The post on the wall is like it asks like it's like not a post but like something to submit.
Oh, this is so strange. Unlike any of my other classes. Let's see. Class wall. No, so the class wall, yeah, you just post a comment. The
I was
discussion,
looking at the welcome to class thing. Sorry.
yeah. So the discuss, like if you go to the forums discussion question, I don't have anything in there. It didn't pre-populate on mine, which is weird. So I'm gonna get to the bottom of that today, right? And I'll let you guys know what's up. All right. Yeah. We talked about that. Yeah, blah, blah. All right, lab safety waiver, right? Make sure you do it. Links in LoudCloud, right? Or you can go to this link, which I've put right here, right? Or I'm gonna throw it in chat in case you guys want to do it and not copy this down. So when we take, you guys can do that whenever you like, but I'm not going to spend time doing it today. If you've done it for another class, just do it again. Right? You got to do it for all classes where it's applicable. All right. So our textbook is called Programmable Logic Controllers 5th Edition by Petrozella. You can get access to the link in LoudCloud once I fix the registration dates. We've got a couple software packages, PLC Logix 5000. There's instructions for downloading it in LoudCloud. We'll go through that the end of this week, beginning of next week, when you guys come to class in case we have to troubleshoot anything. And then there's RS Logix instructions. We're not going to cover them next class because you actually need to be here. It's software that's on a dongle that comes with the PLCs. So we'll talk about that also next week, right? And RS Links Classic, which we will cover. That's part of the RS Logix package, and it's what allows us to link to the PLC. All right. So what things are due, right? We've got lab 1, the push button and LED lab, due on the 17th. We got homework 2. That's not a misprint. Homework 1 is actually listed as homework 2 in LoudCloud, and I didn't want to change the name because in McGraw-Hill. So homework 2 is where we're starting, right? There is no homework 1, okay? 1/24/2021, right? And lab 2 is also due on that same day, okay? So let me pull up, as we're talking about labs, why don't we talk about that right now? I'm going to pull up in a second the lab template. So all the labs are going to be written as technical memos. Okay, so if you go to course materials, you'll see technical memorandum template, right? And you can click on that and wait for it. Oh, that was the wrong one. Wait for it, and I will share my screen. All right, so you guys should all see I should all see this now, right? This is the technical memo template, right? So you want to complete the technical memorandum below in no more than 2 pages. Read the details in each bolded section for information on section requirements, right? So the idea here is that when you get out into the real world, your boss isn't going to ask you for a full-on lab report. They're going to ask you for a short communication that describes what you did and lists the important results. So we're going to write memos, right? So you're going to have to instructor name, from student name, the date that you're submitting it, right? Then regarding the report title, right? Any bullets under there will be topics that were covered inside of your report. These are often used as section headings, right? You're going to have an introduction where you list your group members, so the people that you worked with. Include an introduction to what will be discussed below. List any attached documents. Basically, 1 to 2 sentence overview of your memo, right? Example, Jim, Joe, John, and I worked on this lab, and these are some resources that were included, right? List the topics covered, right? So take these from your bullet points, okay? Process. Discuss the work that was done, right? What were your procedures? Did you run any specific tests? What standards were used to perform the tests? The goal is for the reader to understand your process as it occurred, but not necessarily be able to repeat it step by step. Okay. Outcomes, right? Report and discuss your results. Did everything come out the way you expected? Did the system work? If things did not run or did not turn out as expected, why? What sources of error were present in your system, in your experiment? Action items. How could the sources of error identified be mitigated in the future, right? So how can we help to ease the amount of error that we had? And please contact me /us if you have any questions or comments. Respectfully, student's name, and then references. We're going to use IEEE format for references. Okay, so it's a short report, short and sweet. It doesn't need, if it no longer than 2 pages, no longer than 2 pages. Okay, short, sweet, to the point. This is what we did. This is how we did it. These were the results. These are the things we can do to improve it. Right. Okay. You guys have any questions on the memo format?
Do you want any like screenshots like of the code or anything for like the process? Or just discuss what we did?
That's a good question. If you think that there's something worth having a figure for, that's fine. But don't include something just to have it, right? Make sure that it's value added. Okay. All right, cool. And then we'll go back over here. Okay. So that's the lab template. You guys have that in LoudCloud, right? We're good to go. Obviously, this week it's going to be difficult for us to start to get our, it's going to be hard for us to start the lab. The idea behind lab 1 is this. You're going to be given a PLC. You're going to be given a separate push button, not one of the ones that's already on there. And you're going to be given an LED. And you are going to have to connect the push button and the LED to the PLC and write the code to make it work, right? So you're going to write a simple code where you push the button and the light comes on, and you push the button and the light turns off. Okay, that's what we're going to do. We'll talk about that more, the coding side of that, as we get through this week and next, right? And we're going to do a couple of exercises that will familiarize you with PLC and ladder logic stuff. But the real thing is here that, so my idea here is, in the real world, right, you're going to just be given the PLC and be told you need to hook these things up. So we need to learn how to hook things up, right? Hook up an input, hook up an output. After that, we're going to use more of the PLC trainer functionality that we have already stored for us. All right, so that brings us through the plan. You guys doing all right? We have any questions, comments, concerns, anything?
And we're using the PLC logics. So do you want us to just download that then?
Wait until next class, Logan. Yeah.
Okay.
We're still waiting on one thing from the company about licenses, so don't download it yet. But I'll give complete instructions on how to do it next class. Okay. Cool. And then when you guys get here next week on Tuesday, we'll spend some time, uploading the RS Logics and installing that and getting the PLCs up with our computers. I'm trying to think. I don't know if there's enough PLCs for everybody to have one all the time in class when we're doing labs. But the nice thing about the PLC Logics program is that it has a built-in simulator. So you should be able to write your code and test it before you export it to the PLC through RS Logics. Okay. So that there's at least that. Okay. So first things first, I want to address the rate my professor stuff. Okay. So there's a few things that my rate my professor profile has in common, right? Whether you're looking at the good ones or the bad ones, right? And so what are they and what do they mean, right? So it says tough grader, and it's probably true, right? However, I am going to hold you guys to a high standard, right? People have gotten A's. A's are not impossible, but things have to be perfect for you to get 100, right? 100 is not an A, but perfect is perfect, and small mistakes are small mistakes and things like that, right? Skip class, you won't pass. That's my favorite one. Because you shouldn't skip class, right? So the fastest way for you to lose participation points, which are basically free, 10 points, it's a free 150 points, 15% of your grade for free just for showing up, right? Don't sacrifice those 150 points. Lecture heavy. This class isn't. You guys are going to see. I'm going to lecture basically one day a week, and the other day you guys are going to be doing stuff with the PLCs. Like I said, this is not a class. It's not a class where you are going to benefit from me talking at you a bunch, even though that's all I've done so far. Participation matters. Sure. Again, right? And I would say that being afraid to make a mistake in front of the class almost guarantees that you'll make a mistake on the exam or when it matters, right? So again, there's no exams in here, but mistakes are part of learning. So don't be afraid to make mistakes. And test heavy, that's not even applicable here, right? So don't worry about that. So my suggested keys for success, right, are first off, come to class, right? So don't skip classes. Turn in your work on time, right? Don't leave points on the table. Turn in your work on time. Start your work earlier than you think that you need to, right? So starting late robs you of the amount of time that you have to ask questions if and when you get stuck. So please start a little bit earlier than you think you need to. It includes studying for exams, right? But again, no exams in this class. Unsub from Chegg. Just get rid of it. Don't use the Chegg crutch, right? Come to office hours, right? My unofficial research, right? Totally anecdotal, but I've seen over the last 3 years that students who come to office hours and ask questions and typically do significantly better than those who do not. Is it impossible to do well if you don't come to office hours? No, you can do well if you don't come to office hours. You don't have to, but it ups the odds that you're going to get a better grade because you're getting your questions answered and you're hopefully understanding the material more, right? Okay. All right. So that being said, you guys have any questions on the keys to success or anything? No, probably not. Okay. Now the important stuff. All right. I need you to take a few minutes and complete the quiz at the following link. I'll try my. I will put this link into chat as well if I can find the right one. I have a, there's just so many quizzes, guys. There's just so many quizzes. Okay, let me throw this in the chat really quick. There you go. Here it is. Do this quiz, all right? When you are done, I want you to contemplate and answer the following questions, right? How was your break? Did you do anything interesting? What's your dream job? What's the most boring thing about yourself? And obviously, what are the results of the quiz that you just took? All right. So let's take like 20, 30 minutes and you guys do that. And then we'll report out once. And sorry, Jake. I didn't mean to make you uncomfortable with the BuzzFeed quiz.
It's okay. Don't worry. No offense.
All right, so like 20-ish minutes, and we'll talk about it, right? So we'll hear from everybody, right? So 20 minutes. now at all? Is that better? You know what I mean? All right. You gotta love it when the your microphone mysteriously cuts out. Anyway, problem solved. Miguel, you're the first one on my screen. Unless somebody else wants to share their results, you're gonna get the go ahead.
The results of the test.
Yeah, the really tough quiz that is really earth shattering. We'll go through that, and then the questions that are on the PowerPoint.
All right, so supposedly 31% Ravenclaw, 27% Gryffindor, 22% Slytherin, and 20% Huff and Puff.
Okay. All right. Cool. So.
All right, so for break, I really didn't do much. It was so short, and like I was drained out from last semester that there's no energy to do anything out of the ordinary.
All right. What's
The
your
dream job? Honestly, one day the goal is to work for Tesla.
Okay. Cool. Like what? Just design or test or what? What are you thinking?
Honestly, there's so much that I haven't really looked in specifically, but like just in that general automotive direction.
Okay. Cool. And what is the most boring thing about yourself? Most boring.
I said it in the previous class, but it's like so basic. I've lived in Arizona my whole life, so yeah, I think that's pretty basic.
All right. Cool. Thank you. Appreciate it. We have any other any volunteers now, or should I just keep going through
I'll
on?
go.
Cool.
I'll do it. So, my name's Jake. My break was probably one of the most like regular breaks I think I've had because I pretty much just worked all the way up until actually on each of the holidays. So not a lot there. And then I bet the most interesting thing I did was like probably going out for my job to see the actual on-site construction starting for the substation that I'm the engineer for. So they did a lot of major milestones on that, and that was really neat to see happen finally. It's not just an empty field of dirt for once. And then my dream job, I find myself being like extremely envious of people like Mark Rober and the Stuff Made Here guys and like YouTubers who can just utilize a bunch of their engineering skills and tools to make things that they want that are fun. Because this year when I was unemployed and looking for a new job, I had a lot of free time. So I got a CNC router and I made my own computer case, like started with the CAD model, cut all the panels out, worked on attaching them all. And it was just so fun to me. And when I went back to working, I started missing that a lot. And so I'd like a job where that's what I do is I use my know-how, my knowledge, and my tools I have available to like make things, which I think is basically just research and development engineering, basically somewhere. Maybe it'll end up at a defense contractor working on like satellite systems where that's kind of the whole job, one-off creating what are we going to do about this satellite and how we're going to make it. So the most boring thing about myself, depending on who you ask, I would have thought that it's the fact that me and my wife have gotten into D&D over the holiday season with our friends. I would have thought that was the most boring thing I'd ever heard, but starting to be really, really fun now, especially with the right group. So wouldn't have thought I was one for Dungeons and Dragons, but here I am now buying like custom spell cards from Barnes and Noble to keep. So I've become a nerd officially.
Well, welcome. All right, cool. Anybody else want to go, or should I just start calling people?
I guess I'll go. I was majority Slytherin. My break, it was cool. Just hung out. Dream job, something like automobiles. Design would be cool, but like also like research is also really fun. Just learning new things about different things. I can't whistle. I guess that's kind of boring. And yeah,
All right. Have you tried to whistle?
a lot of times actually, it just doesn't. Nothing comes out.
Okay. Okay. Just checking. Just checking. Cool. Thank you. All right. Anyone?
I'll go. Um, for the quiz, it said I was 40% Gryffindor, 26% Ravenclaw, 20% Slytherin, and 14% Hufflepuff. And then for break, I was really drained at the end of it, but I finally did get the break I needed, the 2 weeks just to like reset. The only interesting thing we did was for New Year's we spent it up in Flagstaff, so got to see snow. That was really fun. My dream job would be either working for some big aerospace company, maybe eventually NASA, or something cool like Tesla, just because even automotive stuff is interesting too sometimes. And then the most boring thing about me, I would say, is I would prefer to stay in instead of going out sometimes.
All right. Cool. Thanks. All right. All right. Well, I'm gonna ask again. Anybody? It's looking like we've got what, 5 more, 6 more?
I'll go. My results said 34 Huffle, 24 Gryffindor, 21 Ravenclaw, and 21 Slytherin. Over break, not a whole lot of anything interesting. If anything, I just went hiking a lot. Dream job, I don't have like a specific company in mind. Used to be like Tesla and stuff like that, but I'm not 100% sure on that after like recent allegations and stuff like that. It'd still be cool. But really just working on something that could make a difference, I think, is mostly what I would strive for. And then most boring thing about myself is that I have like a hole in my gums where my tooth used to be.
Man. Yeah. That sounds like it sucks. I'm sorry.
It's really weird when I brush my teeth on that spot.
Damn. All right. Well, thank you. Thank you. Who wants to go next?
If I can go. So for mine, it says 35% Gryffindor, 26% Ravenclaw, and 20 Hufflepuff, and 19% Slytherin. And for how my break goes, my break was kind of short because I couldn't leave before everybody left, and I had to get here early because of work I have out here. And most of the time for my break, I spend it looking for a car. And for my dream job, I don't have one specific, but I would like to work where I can like make something that can help people, and every year that can change so I can grow with it. And the most boring thing about me, I mostly prefer working and keeping myself busy instead of like doing something fun a lot and like stay in. Like if I don't have work, I usually stay in and like don't do much. So I guess that's kind of boring.
Cool. Thank you. Who's next? All right, I'm gonna pick Alexis. You are the next person on my
For the thing, I was mostly Hufflepuff. And then my break was pretty boring. I didn't really do much. Most exciting thing I did was just like I spent a lot of time just like driving to the beach to like watch the sunset with my sisters. My dream job, I've had like the chance to talk to a lot of like design engineers at Tesla. So just being able to possibly like do that would be really exciting. Most boring thing about myself is I have an obsession with blankets. So I own a lot of like really soft blankets.
Cool. Thanks. Then there's Brandon, Connor, and Logan. Brandon, you're the next one on my screen.
Okay, awesome. You can hear me, correct?
Correct.
Okay. For my quiz, I was 31% Ravenclaw, and my break was really good. Didn't really do anything interesting, just a little bit of hiking and fishing. Dream job, don't know like what specific company, but it would have to be either an aerospace or some sort of military company. And then the most boring thing about myself is I just like to play video games.
Word. Thank you. All right. Connor, you're next.
All right. So I had 33% Slytherin. How was my break? I basically worked until I went home for a week, and then I got stuck in the snow for like basically a week up in Minnesota. It snowed a lot. Dream job is prosthetics. I want to go into prosthetics. And then most boring thing about me is I'm very stereotypical Minnesota playing hockey all my life.
Cool. Thank you. And Logan, what's up?
So for me, I was 36% Slytherin, 28% Gryffindor, 22% Ravenclaw, and 14% Hufflepuff. For my break, I worked at a liquor store, so I got to work Christmas Eve and New Year's Eve, which, by the way, very fun. If anyone was curious. My dream job, I don't have like a specific company, but something where I could like design and work with my hands like most of the day would be really nice. Like be able to design things and see if it will work in a real world applications before like spending the money to buy it, like to build it. And something boring about myself is I don't know, I'm a really big fan of D&D, and my recent purchase for D&D was a bunch of like spell cards for D&D. So I guess that would be my boring thing is I love D&D.
Cool. Thank you. All right, guys. Awesome. Well, it was nice to get to know some of you a little bit better, and nice to meet some of you who I didn't know before. In case you were wondering, right? This was my results. I was Slytherin, Ravenclaw, Gryffindor, Hufflepuff. So that's where we're at. I spent my break grading, then with my family, and then trying to prep on less than a week to get all of these classes ready to go. So that was super fun. Probably not as much fun as working at a liquor store on New Year's Eve, but it's probably up there. Probably up there. My dream job, I'm living it. I'm living the dream right now. Get to teach engineering to young people and hopefully make a difference and help you guys get where you want to go, right? So that's my dream. And a boring thing about me, I mean, so many to choose from, right? I'm just filled with boring. I don't know. I drive 45 minutes to work and from work every day. That's probably the most boring thing that I do every day. So there's that, right? Cool. And yes, I do. I find my results acceptable and fairly accurate. So there's that. Anyway, so that's it. That's the fun stuff. We'll get a little bit into topic one. We'll talk about some of the objectives, and then we'll jump into some more of the textbook. I don't know if you guys could hear me when I said this, but I did fix the issue with McGraw-Hill. So if somebody wanted to check that out and see if that's allowing you to register now, it should. I changed the dates. And last thing is the room for this class is going to be not 1304, but 1336. And we're gonna go to 1336. Awesome.
It works, by the way.
Awesome. Thank you, Logan. All right, so I don't know where that came from. Topic one. All right, so topic one is the overview of controls and instrumentation. So some of the stuff we're going to talk about over the next week is not necessarily specifically stated in your textbook, okay, when we're talking about controls. But this is just to give you a broad scope idea about how controls work and what they are, right? The instrumentation part of this is going to come in when we start talking about sensors, and there's a whole topic on sensors and transducers that we'll get into later. And one of your guys' the one benchmark assignment in the class is connecting a thermocouple or a thermistor to your PLC and actually have it do something when you hit a temperature threshold, right? So we'll dunk it in a cold water bath. We'll make sure that our PLC activates the way that we said it was going to. We'll dunk it in a hot water bath and do the same thing, right? So it's kind of like an HVAC problem, right? You've got some temperature you hit, you want the heat to turn on, or you have some temperature you hit and you want your air conditioning to turn on, right? Something like that. But we'll talk more about that when we get there. The topic objectives are as follows, right? We want to identify a control system and its components. We want to describe how feedback is used in control systems. We want to explain how feedback can influence the stability of a control system. And we want to describe how programmable logic controllers, or PLCs, are used to implement control systems. Okay, so that's that part. So electronic systems. Any questions on the objectives? Right, those are just from the syllabus. You can grab them if you want them. All right.
Oh, sorry.
Yeah, no, what's up?
I don't know if it matters, but all the learn smarts are past due. I don't know if it matters, but
It doesn't. They're not for points.
okay.
They're for you guys to have them. So
Okay.
So don't worry about that. All the homeworks are correct dates, as they should line up with everything that is in LabCloud. So yeah, learn smarts are optional. If you want to go through them, you can, but you don't have to. All homework is going to be done through McGraw-Hill, just like in MET 213, right? So there's that, except that these are more how do I want to say this? More knowledge based and less calculation based, right? Okay, so what is an electronic system? What is it? Also, so before anybody answers, I see you're chomping at the bit to do so, but before anyone answers, please don't say a system that uses electronics. That's like my pet peeve is when you give me the words in the definition, right? So what is an electronic system?
I'll go.
Sure.
Electronic system is a system in which I would say there are inputs and outputs that are processed electronically.
Sure.
And I'll leave it there.
Right. So yes, right. It's a physical interconnection of components and parts that gather various amounts of information together, right? So you have your inputs, it's gathered in some way, it is either transmitted or stored electronically, right? An electromechanical system is one in which we take electrical energy to produce a mechanical result or mechanical energy to produce an electrical result, right? So what are the basic components of an electrical system? If we're talking about the physical interconnection of components or parts, what would these components be in an electrical system?
An on and off switch.
Okay, an on-off switch. Think
A conducting medium.
so you guys are both right there, right? Think so. I want you to think less high level, right? I want you to get a little bit more detail oriented. And Jake, I want you to bring it up maybe a level. Like, what is the basic component of an electrical system, right?
Conductors or wires.
Sure. All right. That's part of it. Like, what are the wires connecting?
Components. Oh, that's part of the thing.
Power supply.
Your resistors, your
To the
inductors,
circuit
and your
board?
capacitors, and everything in between.
There you guys go. You guys got it, right? So hold on. It'll get there. Resistors, capacitors, inductors, right? Yeah. Right. The basic components, the basic building blocks for any electrical system, which is typically what we call a circuit, right? Are going to be these things, right? So, you know, well, not all other components, but many other components that we discuss when we have an electronic system are just made of arrangements of resistors, capacitors, and inductors, right? That's what we're on. So a simple electronic system has an input, a process or a plant, and an output. Okay. So like Jake said earlier, right? You have some input, it gets processed in some way, and then we produce some result, right? So going back to the HVAC thing I was talking about when talking about the benchmark, right? You take in some temperature, all right, so if you're talking about your thermostat, right? You set it to 70. You compare that set point temperature to the temperature that you're reading in the room. And if it's less than 70, something happens, right? Less than 70, the heat turns on. That's your output, right? So when we're talking about a process or a plant, we're talking about what are we doing with this input? How does this input affect the system to produce the output, right? And we can represent that in a number of different ways. When you talk about this mathematically, right, which is, the equations, we took circuits, we can do our circuit equations, come up with those things, right? We can do our Ohm's law and our Kirchhoff's laws and run those numbers, right? We could do it descriptively, right? You can use words, or we can do it pictorially with what we call block diagrams. And a block diagram is what we have right here on the right. We call this a block diagram. Why? Because there's some block that has an input and an output, or a series of inputs and outputs, right? So in its simplest form, we have what we call a single input, single output block diagram, right? Which is not what's drawn here. A single input, single output would look like this, right? So you've got the block. The block is a process or a plant, typically denoted by G of S, right? Which is for a transfer function, which we're not really going to get into in here, but that's where we're at, right? So this is my input. It goes into this block, and I get some output, right? So in its most basic form, that is a single input, single output block diagram. Now we can have multiple input, multiple output, right? Which what we call a MIMO system, M-I-M-O. And that's what this looks like down here, right? We've got some system or some process, and you've got multiple inputs that come in and multiple outputs that come out, right? And that's obviously more complex, right? So it all depends on what kind of system we have and what we're trying to do, right? Could be some certain batch processes that require you to have heating data, and so all right, let's make one up, right? I've got a batch mixing process, right? What are my inputs? Well, I need to know how much of material A I have, how much of material B I have. I have to control the amounts of those two things. I need to know what the temperature inside of the tank is, because if I'm mixing things, potentially I need it to be at a different temperature than when it comes out, right? So you could have very complex systems that have multiple inputs and then produce either a single or multiple outputs. Right? Electronic systems are typically represented using block diagrams, at least from a control systems point of view. Okay. You can take a very complex electronic system and you can represent it as a combination of simple blocks, right? So this multiple input, multiple output system, we could break this down, right? We could break this down into a series potentially of multiple single input, single output systems, right? We could potentially, depends on the system. But electronic systems have inputs and outputs. And what is an input and what's an output? Well, I want you guys to think about inputs and outputs as the cause and the effect, okay? Your input is the cause, and whatever happens is the effect, right? Your output's going to be the effect of that, right? I set my temperature to 70 degrees. My input is a temperature of 68 degrees. My effect is that the heat turns on, right? The cause and the effect, the input and the output. All right, so you don't have groups because we're not sitting at tables right now, and that's fine. But I want you guys to take a couple minutes, and I want you to think about inputs, 3 different inputs potentially for this system, right, as pictured right here, and what the corresponding outputs would be. All right, so instead of 3, think of 1, right? 1 input and 1 output for this system. All right, start with 1. So we want an input and we want an output for this system. First of all, does everybody know what that system is? What this thing here is pictured?
Is that like a portable speaker? Something by the hand, like a Bluetooth one?
Yeah, it's a portable amp, right? Amp speaker combo. So what's an input for this? See if we can get a couple.
Like the power source going into it.
Okay. So what would be the output?
Wouldn't it just be the sound coming out of it?
So if the input's the power, right?
Right.
Power. What's the effect of applying power to the system?
The purpose of it is to make sound, so the power is creating the sound. Isn't it?
So I would say that the effect of the power is that it energizes it, right? It gets it ready. It puts it in standby. But that's certainly an input. If we're talking about sound as being the output, what would we need for the input?
I'll go.
Yes.
So the volume knob is adjusting a potentiometer, but to the system, what the system at that point is going to see is an adjustment of voltage through that potentiometer. So the input is that adjustable voltage, and then consequently, the output for the volume is going to be the amplitude of the sound waves coming out, which is technically the voltage too of that. So your input is the voltage from through the potentiometer or the volume knob, and your output is the amplitude through which the speaker diaphragm has to be powered.
Sure. Yeah. What about the most basic input output pairing that I think Leo was getting at here? Right. So in the most basic sense of this, right, you've got what going in and what coming out. So you've got what, right? If this is a Bluetooth speaker, or if this is, some sort of portable amp speaker combo, right? What are you going to use it for?
To produce sound louder.
Right, to produce sound, right? So if you're going to produce sound, what do you need to put into it? Right? If you're going to amplify the sound, what did you put in to start with?
Your audio signal that you're putting in from your instrument or phone or whatever you want.
Yeah, put the sound in, right? Put sound in, you get louder sound out, right? That's the most basic level of this, right? Now you can get crazy with it, and you could go down to component levels and say, yeah, you adjust the potentiometer. That's exactly how you change the sound, right? You're either restricting or increasing the amount of voltage signal that you are allowing out, right? And on its most basic level, right, this thing takes vibration and it amplifies that vibration, right? And makes it louder or less loud if you're going to turn the volume down, right? But that's it. All right, what about this one? Right? What's an input for this system, and what would the corresponding output be?
Dead dinosaurs can directly convert into speed. It's incredible.
Sure. Yeah. Take your gasoline as the input, right? And you get motion as the output, right? What's something else that's less obvious for this one?
Some of the newer cars have like motion sensors on the side, so like if it's approaching something too close on either side, it will adjust the car to like move away from it or alert you that you're getting too close.
Yes, absolutely, right? Newer model cars have all those fancy bells and whistles, right? Where you've got lane departures, and the car is a really complex system nowadays, right? But yeah, so we'll talk a little bit about how cruise control works too, because that's a really common control system that a lot of people use on a daily basis, right? What about this? What about this then? What's an input and an output for this? Going back to the car though for a second too. I was thinking another really obvious input output pairing for this that we take for granted is you turn the wheel right, and the wheels turn to the right. If you turn the wheel left, the wheels go to the left, right? So inputs and outputs don't have to be environmental signals, right? They can be user defined inputs as well, right? Okay. So what about this guy? What about this digger? What's an input and an output pairing for this?
The ignition or the on switch, depending on the type.
Sure. Turns on. You turn the switch and the thing turns on, right?
The levers you pull down or up will control the the claw making it go down or up as well.
Right? There's some user control in there. Right? You've got to, you know, I mean, ideally you wouldn't just hop in there and start messing around, but like, you know, you could and probably figure out how to use it, right? But yeah, you've got all sorts of levers for raising and lowering the different joints, right? And they each articulate independently too, right? So I can lift this, I can rotate this back part without having to rotate here, right? Or I could just rotate up here and leave this in position, right? So there's all sorts, and even the basket itself, right? You can control the angle of that basket as well, right? So there's a lot of different things here, and you know, obviously it moves back and forth, right? You can drive it, so there's those controls as well. All right, cool. So that's inputs and outputs, right? Inputs and outputs aren't too bad really to get our head around, I don't think. We can also talk about the types of signals that we use when we're talking about electronic systems. All right, so we typically classify the types of signals in two ways. We either have continuous or discrete. And continuous signals are also known as analog signals, right? And these are continuous time signals that are defined at all points in time. So something like this plot right here, right? This guy up here. Right? This is a continuous time system, right? It's nice, it's smooth. We have all the data for every single time point, right? It looks great. We also have discrete or digital signals, and discrete or digital signals are defined only at specific discrete time points. And this is what we call our sampling rate, right? And so you can see that same signal, if we had it as a discrete signal instead of a continuous, right? That's the plot below. You get data points at specific intervals, right? And that's nice, right? So what are the pros and cons, right? So the pro of having an analog system is that you get all of the data, right? But the con of the analog system is that you have to store all of the data. Now, for something that's 10 seconds long, this is trivial, right? But if you want all of the data for, you know, I don't know, let's say fuel consumption of a flight from Australia to California, right? Now you're talking about all the data for an 8-hour flight, right? Probably longer. But that's a lot of data that you need to store, right? How are you going to store that reliably? Well, discrete time systems are nice for that, right? Because we only take data at certain time points. But the issue with discrete time systems is, what if you don't use a high enough sampling rate? Okay, so what if we took our sampling rate and we cut it in half, right? So we're only getting every other point here, right? So instead of getting all the blue dots, I'm just getting the green ones, right? Is that going to give me a good enough picture of what this looks like?
Yeah.
Probably. It's probably not that bad, right? What if I only get one in every 4 points, right? And I'm probably not grabbing all the right ones, but you get the point. What about that? Is that going to be as good as, right, if I take half of what I just did, right? That still gives me a decent picture, right? Like if I connect these dots, oh, but I start to lose some of my signal here, right? So the problem here is that if I don't take a high enough sampling rate, I lose parts of my signal, and I get a signal that's not necessarily representative of, right, of what I'm talking about, right? So if I took this every 2 seconds, right, I would get a signal that looks like that, right? Which no longer looks like that, right? So the idea here is that we need to identify a sampling rate that is appropriate, that gives us, so the art of digital systems is defining a sampling rate that gives us the amount of data that we need with no extra, right? And there's ways that we can do that, but that's a little bit beyond the scope of this class. Right now, what we need to know is just the difference between something that's digital and something that's analog, and when it would be appropriate to use the different types of signals. Okay. Notice these block diagrams don't really change much for each type of system, right? We've got an input-output pair for a continuous time system, which is a function of t, right, or time. And we've got the discrete time system, which is a function of n. N is not time, but the number of points, which is time in a sense, right? But slightly different. You guys have any questions on continuous versus discrete right now? No. All right. You guys doing all right? No questions? No. All right. Practically speaking, block diagrams make it very nice for us to combine larger, more complex systems by using a simpler subsystem. Okay? So complex system can be combined in series, in parallel, or in feedback. And we'll talk about what these mean. But in series, I think makes sense here, right? This is a series connection because there's one right after the other, right? Much like two resistors in series, or two inductors in series, or two capacitors in series, right? These are in series. Okay. Turns out that if you wanted to combine two systems that are in series, it's pretty easy. But let's talk about what this actually means, right? I've got my input X. This goes into my first process. It outputs something, which is then the input to my next process, and it comes out, right? So in the real world, what would this be, right? All right, let's say this is a bottling line, right? First thing first, bottle goes into the first process. It gets washed, comes out, goes into the second process where it gets filled. Well, probably going to get dried first. Where it gets dried, dry bottle comes out. Okay? That would be a real world system, right? That's in series. There are things that happen sequentially, and one has to come after the other, right? Because of the way this is defined. But what if I don't care, right? What if I don't care that these two things, I don't really care what happens in between these two things. I just want to know, how does my input relate directly to my output? How does my input X relate directly to my output Y? Well, if I wanted to combine these two things, right, it just becomes this, right? So I've got some input, X of T. I apologize for my handwriting in advance. This computer, I'm going to blame the computer screen being at a weird angle. That'll be fine. All right. So I just want an equivalent system of one block. All right. So how do I make that happen? Well, when two things are in series, we can just multiply them together. So if you multiply these two blocks together, right? Because remember, and I don't think I actually stated this when we started talking about block diagrams. Block diagrams are a graphical representation of the math. Okay? They're a graphical representation of the math that we are doing. Now, I'm going to preface all of this by saying that we are not going to go super deep into all of this control system stuff, but it's important to do the setup so that we understand how these systems behave, okay, and how control systems behave. Okay, so if you have two things in series, you can take both of these plants and combine them together by multiplying. All right, so the real world example I use of this bottling process, what is that? Well, let's think about it a different way. What if this was an electromechanical system? Okay, so say G1 represents a motor, right, or the electrical components of a motor, and G2 represents the mechanical components of said motor, right? I put some current in, X of T, I put some current in to the motor. What happens? Well, the motor is basically just an RLC circuit, right? Or an RL circuit, and it's very, it's just an RL circuit, it's very basic, right? So you put that current in, it stores energy in the inductor. The inductor creates a magnetic field. The magnetic field affects the mechanical components and causes the motor to spin, right? That's how it works. So there's some mathematical equation, G1 here, that describes the electronic system, right? That describes that circuit. And there's some mechanical equation that describes the torque being produced on the mechanical components in G2, right? And it turns out if I multiply those two equations together, I can tell you the direct relationship between the input current and the output velocity or position of my motor. Okay. Now, that's, again, above the pay grade of this, but that's the idea behind what makes block diagrams useful, right? Because you can either look at just the electronic components or just the mechanical components. Okay. All right. You have any questions on this? Anybody? All right. So I'm actually going to erase this because it should come up anyway. Because it's going to look nicer when it looks like this. Okay. So I take some input. When things are in series, we just multiply them together and I get my output. Okay. Another way of thinking about this equation that we're writing here, right? This is telling us that, well, let me rewrite this, right? I'm going to call this total thing, so I don't have to write G1. I'm going to call this H of S for a second, okay? So X of T times H of S is equal to Y of T. All right, so this is saying that my input times the magic equation that I have inside of my block here, which I call a transfer function. All right, the input times my transfer function is equal to the output. That is what this, when we look at this, that is what it is telling us. Okay? And that's series connection. So how do we deal with parallel connections? Right? So two processes that happen simultaneously. Right? When processes happen in parallel, they're happening at the same time, right? If you go back to the original slides, right, where the original like get to know you slides where I show you guys my timeline of work, right? I was working on getting my master's degree and doing and working at Picatinny Arsenal in parallel, right? Those two things were happening at the same time, right? In circuitry, right, this is to say that we have, two portions of our circuit that are energizing at the same time, and both of those things combine, right? Right here, this circle with the plus sign, that's what we call a summing junction. They both get added together to give me y of t, right, to give me my output. Okay. All right. So again, we have G1 and G2. These both represent different things. So how do we combine two parallel processes? Well, you can see it here, right? Instead of multiplying them, we need to add them, and we have to add them using the summing junction, right? So we add them using the summing junction, right? So how do we simplify that block diagram? Well, same way that we did it before, right? Except that instead of multiplying the two transfer functions, we add them. So we have two things in parallel. We have to include a summing junction. Now, here's the thing about summing junctions. They're typically on any diagram given as a circle, where you'll have some input and a couple of inputs, right, and some output, right? And typically you'll see them written with positive signs, right, for adding, right? So, right, so let's draw this again. All right, here's some input that I have. Here's a second input, and my output will be in blue, right? But say instead of adding them, right, I have one that's positive and one that's negative, right? We can subtract things through a summing junction as well. The typical rule of thumb is that if you do not put a sign there, everyone will assume that everything is supposed to be positive. The most well annotated ones will have a positive and a negative sign, or will give each signal their appropriate sign. But sometimes it gets really hectic to do that, right? And so typically what you'll see is that they'll leave most of them blank unless there's a negative that has to be there, unless you're subtracting. Why is this important? Well, this is going to get important when we start talking about feedback systems in a second, and whether something is positive feedback or negative feedback, right? But the idea here, right, remember, if we're in series, they get multiplied, and if they're in parallel, we need to add a summing junction in order to put them together. All right. Everybody cool with parallel? All right. So let's talk about feedback. This is a closed loop feedback system. Why is it called a closed loop feedback system? Well, because it's like a closed loop, right? So you see this part right here. So the signal, how does the signal flow, right? Here's my input. It goes this way, and then it branches off and comes back, and it feeds back into this junction here, which is typically a summing junction, right? So, right? So it kind of forms this loop of signal, right? It forms this loop of signal. These lights are getting me. Got it. So what happens, right? Why would we use feedback? Well, we actually use feedback all the time. And I've talked about a couple of examples that you use in your daily life, right? We've talked about your thermostat. That's probably the most common feedback system, right? You set a temperature, right? You set, I want my house, apartment, dorm room to be 70 degrees, right? And you either have to set heat or cool on most thermostats, right? Some fancy thermostats will do both, right? But most of them, you have to set heat or cool, right? So if you turn on your heat, you're saying anytime I dip below 70, I want this to turn on, and I want it to bring it back up to 70 degrees, right? So what is that doing, right? That's starting here, and you're setting your input, right? My input is 70 degrees. This signal travels here. It goes into this, right? It says, well, the actual temperature is 65 degrees. Output, 65 degrees. I feed that 65 degrees back into my summing junction, and I compare these two values. Typically, for a negative feedback system, you'll subtract them, right? For negative feedback, you have 70 minus 65. It's going to be a 5-degree difference. Because that number is not 0, it's going to turn the heat on. And it will do that loop until this number is 0. Okay? Now, there's a part of this, right? So this in here, we typically give it the letter E, that signal. And it stands for error. We call that the error of the system. Okay? The error in the signal. And we want error to be 0. It's the same way that your cruise control works in your car, right? Set your cruise control, to 70, and you just sit there, right? And what's it doing? Well, it's comparing that set point, that x of t that you set, to how fast your car is actually going, right? And, if you start going uphill, it'll give it more gas so that it stays at 70. And if you start going downhill, it applies the brake so that you stay at 70, right? And it's continuously comparing what you set to the actual system speed, right? The actual speed of your car. So the thing about feedback systems, right? Hold on. Okay. So there's two types of feedback systems, right? I just described to you what we call a negative feedback system, right? And a negative feedback system is called that because if you look at the summing junction, right, so I'll draw a system here. I'll feed back. If you look at the summing junction, this signal is being subtracted. A positive feedback system adds this reference signal, right? It adds this feedback signal to the set point. Okay? That's the difference. What is the issue here, right? Is one of these better than the other? Typically, we prefer to run with negative feedback systems, right? And the most common type of positive feedback that I can illustrate for you is when you have noise on a PA system, right? As Will Ferrell would say, when you have a hot mic, right? So when you get that screeching in there, when you're too close to your PA, when you're too close to the speaker with the microphone, what's happening? I'm talking into the microphone, right? Talking in my microphone, but then the speaker of my own voice goes back into the microphone, right? And as I'm talking, the signal that I'm projecting is also getting fed back into the microphone, and it goes on and on and on until it gets louder and louder and louder and louder until either you turn it off or your speaker blows, right? One or the other. And so that's an example of positive feedback, right? You're continuously adding signal into your system, and that's going to cause it to grow and grow and grow and tend to go unstable, right? That's positive feedback. Negative feedback, we're taking something away every time we do this loop, right? We're taking something away. And so it doesn't impact it in the same way. Okay. You guys have any questions on feedback, parallel, or series blocks? We're going to talk about these a little bit more later in the semester as well, right? We'll talk about how we can implement some controls in a PLC too. So any subsystem can be represented as a simple block diagram with an input and an output, right? We talked about this already, right? And the transfer function is just the ratio of my input to my output. Or I'm sorry, my output to my input, right? So it's this fraction, right? Where theta O is my output and theta I is my input, right? And this has to equal G of S, right? I wrote this down earlier, remember? But this stems from this equation, right? We're just rearranging that algebraically, right? So these two things, these two statements are equivalent. It's just how I'm representing it, okay? So I want you guys to take a couple minutes, and I would like you to simplify this block diagram, please. What do we think? Based on the rules that we just came up with. What I'm gonna do is I'm gonna turn on the annotation. You guys should be able to annotate on the screen, and somebody please draw the equivalent block diagram for this once you get it. Be able to draw it right underneath. If you can't get to annotate on your toolbar, there should be a button that says annotate, and you should be able to draw with your mouse. Just click the button. Nice. Thank you, Miguel. Nice. Yeah, that's it, right? It's in series. You just multiply them all together. Also, I'd like to say your handwriting is better than mine. Did you use a mouse for that? Because I'm using a pen. Okay, all right, gotcha. I was gonna say with a mouse, I was really impressed. Really impressed.
No, it's with the pen. With the mouse, it's impossible.
All right, solid. Thank you. Yeah, that's exactly it, right? So with a block diagram in series, all we have to do, right, is just do that, right? And I wrote it down there as M of S, right? But that's just G times H times F of S, right? So often what you'll see is you'll just see one variable inside of the block diagram, right? But we know that that's just R times H times F of S. We have time for one more, I think. All right, this one's a little trickier. I'm gonna have to. So this one's a little trickier, but let's try this one. Right. So let's try this one. Simplify what you can. Right? Simplify what you can. That's weird. All right. So this one's a little bit trickier, right? A little bit trickier. And I probably didn't prepare you enough for it, but oh well. Okay. So what we got? What's the first thing you guys think you should do here? Start there. What's the low hanging fruit? mean, Miguel already gave you the answer for part of it on the last slide, right?
I guess multiply GS, HS, and FS.
Right. So we can take all of this and we can you guys hear me now? Very strange. Just automatically cut itself off. All right. So we're going to combine all those, right? And we know that on the last slide, we called that M of S, but I'm going to combine all these, right? I'm going to call this F of S for right now, right? So F of S is just G of S times H of S. All right, I guess F was a poor choice because there's already an F. J of S, all right? This is J of S. Okay, so it's just G times H times F. That's what J is. Okay, but this leaves us with a very interesting scenario, right? This leaves us with J of S exporting C of S. We feed it back. We've got L of S down here. This goes into a summing junction. We were told that it's negative. Right? Whoa, don't want that. Right? So this is what we have. So now we have something that's in parallel, but it's not truly parallel, right? And so here's where we can do something interesting, right? So what do I know? What do I know about this? Okay. Well, I can break this down into the individual.
Your mic cut out again.
You guys hear me now?
Yes.
All right, I switched mics. Apparently, this one doesn't want to behave for me right now. That's fine. It's fine. All right. So this is interesting, right? And as you guys know, when a professor says that something's interesting, it's probably not really interesting for you, but I think it's interesting. So anyway, let's look at this. Well, what is C of S, right? Well, C of S is my output signal, but C of S, right? I can write an equation for C of S, and C of S is just my error, E of S, times J of S, right? Because C of S comes out of the J of S block, and E of S goes into the J of S block, right? So E times J has to be C, right? But I also know that E of S, which is coming out of this summing junction here, right? This guy, has to be equal to R of S, right? My reference signal, plus L of S times C of S. So what's my goal here? Well, my goal here is to get everything in terms of R of S and C of S, right? Why? Because that's my input and that's my output. And those are the only two things that I really care about. So I'm going to do some algebra here, right? And I'm going to say, well, if I take this equation on the top and I say E of S is just equal to C of S over J of S, right? And I can plug this in over here. All right, so I'll plug that in over there. So let's do that. C of S over J of S is equal to R of S. I apologize for my handwriting right now. It might get better. It probably won't. So that says C of S over J of S is equal to R of S plus L of S times C of S. Okay? Cool. Cool. So now we're in algebra, right? And I want to get R of S on one side by itself and C of S on the other side by itself, right? So we'll algebra a little bit more and multiply through by J of S, right? So I'll get J of S times R of S is equal to negative L of S, C of S, J of S, plus C of S. Does everybody see where that comes from? Everybody following my algebra right now? This is the long way around, right? This is the long way around. All right, so all I did was multiply through by J of S, and then I subtracted over LS, CS, JS from C of S, right? One more thing here. So we end up with, let's do it this way. We end up with, I'm going to erase this part over here since I've run out of room. All right. What do we end up with? Well, we end up with 1 minus LS JS times C of S is equal to J of S times R of S. But what we really want is an equation for our output. So C of S is equal to J of S over 1 minus L of S, J of S, whole thing times R of S. And there it is. That's the combined block diagram. Okay. So really, all we had to do, right, how we had to start this was we first collapse this top part, right? What we really want is we want everything in a feedback system to be in this format of that green block diagram that I drew at the top. All right? Why? Because it turns out for a negative feedback system, this will always hold true. All right? What about for positive? If I had a positive feedback system, how would this change? That sign in here, this guy, that would be positive instead of negative. You do the math the same way, and you could prove it out if you wanted to. But whenever, so, right? So what's the point of that? Well, now we know that we can simplify that all the way down to a single block, input, output, right? Because this is my transfer function for the entire system. The thing I just circled in blue. All right, so what's the bottom line? What do you guys need to take away from this? Do we need to know how to do block diagram algebra? Not really, not really. The rest of this class, we're not going to really touch that again. But what do you need to take out of it? What I would like for you to take out of it is understanding where the concept of what the concept of a feedback system is and how we use a feedback system in practice, right? What's the difference between a negative and a positive feedback system? and why would we want to use one versus the other, right? That's what we really want to get at. We're not going to go much more. We're not going to go into any more depth or detail than this on how to use block diagrams. And you'll even see the first homework has nothing to do with this. So there's that. All right. But now you know it, I guess. All right. You guys have any questions? When in doubt, if you ever see this and somebody's like, hey, I need you to simplify this block diagram, start with the parts that you know how to do, and then start identifying the different signals, right? And just try to make an equation. And then you can draw it again. All right. All right. Any questions? No? I swear it'll be more fun than this when we get into the classroom. I swear. I know the METs, you guys are like, not again. He said this was going to be different than 213. I know. I did. I said it. It will be. I'm limited on what we can do when you guys are not in the classroom now. All right. So that being said, check out the reading from the LoudCloud link, right? This actually, none of this is in your textbook that we just did today. The stuff that we're starting next class will be, okay? Please check out the Learn Smart for Chapter 1. We are going to look at the homework, see if you have any questions. Come to office hours, right? You have the link for the office hours. You've got all the different links you need. Join the Discord server, please. It's beneficial. Okay. When you get there, just let me know who you are. Okay. I know right now nobody's excited for this class. It will get better, I promise. Promise. Won't be like this every time. All right. That's all that I've got for today. Oh, good. Please hold. Nothing like this. So those of you who've had me before, I put up a poll everywhere at the end of class. I would like for you to let me know what you found to be the most confusing thing for the day. Okay, so it is We Live. There you go. Please go to polleverywhere.com. I mean, we had a pretty even split from the Hogswort houses today, but it did look like Slytherin did come out on top. All right, so just be aware. Connor, the way that you're sitting right now, that poster looks like you have a party hat on top of your other hat. Just to let you know. All right, guys, I swear it's going to be a fun semester. I swear we're going to do a lot of fun stuff with PLCs and making lights turn on and all that, right? But that'll probably be next week when we're in the classroom, right? So next class, we'll talk a little bit more about some terminology from the textbook, and then we are going to go through and attempt to install some software. All right. Cool. That's all I've got for today. And I'll see you guys on Thursday.
Good day, Professor.
Have a good one, Professor.